Okay, now let's go on to question 5. It says a boy holds the loose end of a long rope which is fixed to a pole. Okay, he moves it up and down at a rate of 20. Okay, 20 complete oscillation in every 50 seconds. So this is the number of oscillation. This is the time it takes. Okay, time taken for 20 oscillation. Okay, figure 8.1 shows a section of wave moving along the rope. So this is the displacement. So on the y-axis, this is the displacement. On the x-axis, this is the displacement, but it's actually the distance away from the pole. Okay, so this is the displacement distance graph. This is actually a displacement distance graph. They ask you to state the value of the amplitude of the wave. So amplitude is actually the highest displacement from rest position. Now, if the rope was at rest position, how would it look? It will actually look like this. Okay, sorry for this freehand drawing, but yep, it will look like this. So what is its value here when it is at the rest position? It's actually 15. Okay, so the amplitude will actually be from the rest position all the way up, or from the rest position all the way down. If you were to take your measurement here, this will be the value of the amplitude will actually be 15 cm. Okay, so 30 to 15, 15 cm, 0 to 15, 15 cm. State the frequency of the wave. So to find the frequency of the wave, what is frequency? Frequency is the number of waves or number of complete oscillation in 1 second. So we know that there's 20 oscillation in 50 seconds. Okay, so what we need to do is in 1 second, it will be 20 over 50. So therefore, frequency is actually 20 divided by 50. What we're going to get is 0.40 hertz. 0.40. Now, calculate the speed of the wave. Well, to find the speed of the wave, because this is a wave question, we most probably will use V equals to F lambda. Lambda is the wavelength. Now, we have the frequency, which is 0.40. How can we find the wavelength? So if you look at this question here, wavelength is actually the length of one complete wave. So let's use a different color to show. Can you see this blue color? Okay, this blue color line over here. This is one complete wave, and one complete wave is actually from 0 all the way to 60. So the speed of the wave will actually be 0.40 multiplied by 60. Okay, so if I press our calculator, 0.4 multiplied by 60, what you're going to get is 24. Do take note, because 60 is in cm, so it's actually 24 cm per second. Now, I realized they 1 meter per second. There are two ways to go about this. So if this is cm per second, I can just take this to divide by 100. Then I can get 0.24 meter per second. The other way is I convert this 60 to meters first. So if I were to rewrite it here, it will be 0.40 multiplied by 60 divided by 100. The final answer will be 0.24 meter per second. So 0.24 meter per second. Now in part B, it says, figure 8.2 shows the cone of a loudspeaker that's producing sound wave in air. At any given time, a series of compression and refraction exists along the line PQ. Okay, so why part B and part A, they're linked is because it's still on the same idea of waves. Okay, it says the sound wave experiences a refraction at P. Okay, so at P, it starts off a refraction. Now, it says on figure 5.2, so this is supposed to be 5.2. Draw the wave lines to represent two wavelengths of compression and refraction between P and Q. Okay, so wave lines, we know that it's a refraction here. Okay, so this is a refraction. We know that we want two wavelengths. So one refraction to the next refraction to the next refraction. So total there should be 3 refraction here. so that we can have two wavelengths. Okay, so this is a reflection to a reflection to a reflection. So you can see here, one reflection to the next reflection, this is one wavelength. The next one reflection to the next, this two wavelengths. So two wavelengths over here. But in between reflections, there's actually compressions. So this line will actually be compression. This line will actually be compression. So now it's not just about this RC kind of thing. Okay. Uh, oh, actually that's all we need to. So reflection, compression. So it will be something like this. Quite simple to do. In part 2, it says, with reference to the sound traveling along PQ in figure 5.2, explain what is meant by a longitudinal line. Okay, so longitudinal wave is a wave, okay, in which the direction of vibration is parallel to the direction of wave travel. So in this case here, to be very precise, the direction of vibration is left and right. The direction of wave travel is towards right. Okay, so at any one point, if there's a particle over here, particle over here, so the vibration particle, let me use blue, will be going left and right. Wave travel, so this is a direction of vibration. Direction of wave travel, maybe let me use green. So wave travel is actually this direction. So you can see here that the direction of vibration is parallel to the direction of wave travel. Now let's go on to part 3. To the right of Q, there's a large vertical wall 50 meters in front of loudspeaker. So there's a wall over here. The distance between the loudspeaker all the way to here is 50 meters. The speed of sound is 340 meters per second. Calculate the time taken for the echo to return to P. So the key here is an echo. So the distance traveled by the sound will actually be equals to 50 multiplied by 2, 100 meters. So the sound will have to travel 100 meters first. So the time taken, so we know that speed equals to distance over time. We know that speed is 340. We know that distance is 100. We know that time is the one that we'll calculate. So T is equals to 100 divided by 340. So if I take 100 divided by 340, what I'm going to get is 0.294 seconds. Okay, so final answer in 3SF. Okay, so that's for question 5.